Now that we've seen how to solve linear equations and how to graph linear equations, we're going to move on to systems of linear equations. And with a system of linear equations, which looks like this, we have two separate linear equations that we actually are going to consider together simultaneously by this brace here. This brace says look at these at the same time and find the solution that satisfies both simultaneously. And there's several different techniques for solving systems of linear equations, and we're going to begin by looking at graphing. Now when we graph a linear equation, we see a line. And you can imagine if we graph two linear equations, we're going to see two lines. And the solution to the system is the point where those two lines intersect. So we're going to have to recall how to solve linear equations eventually, but for right now we want to focus on graphing linear equations. So let's take a look at these two equations, and because we're dealing with two things at the same time and we can get confused as to which is which, I'm actually going to color code these. So I'm going to say the first equation is going to be blue, so everything in here that's going to be blue is about that first equation, and everything that I write in red is in regards to the second. Now when I go to graph a linear equation, if I have slope-intercept form like I do here, it's going to be very quick for me to graph. I can see the slopes and I can see the y-intercepts right off the bat. Let's go ahead and write that information down. So for the blue line, the slope is the coefficient on x, the number in front of x, which is an implied -1. When I don't see that coefficient, there's a 1 there. So -1 is the slope. The y-intercept for that line is going to be the point 0, comma, whatever the constant is. So in this case, it's -1. For the red line, we can look for the same information. The slope, again, is the number in front of x. It's that coefficient, which in this case is 2. And again, for that red line, the y-intercept, which is the point where the line touches the y-axis, it's always going to be the point 0, comma, whatever the constant is, which in this case is 5. So I've got the pieces of information that I need to get my graphs of these two lines. Let's go ahead and do that. For the blue line, let's begin there. The y-intercept is 0, -1, so I don't go left or right, I simply go down 1. So there's my starting point for the blue line, and from there I use the slope to help me figure out how to count up or down, left or right, to get additional points for additional accuracy. And what we'd seen in a previous video is that if we thought of the slope not just as that number or that coefficient, but actually thought of it as a fraction, rise over run, it's a little more helpful for us to get the additional points. So what I'm going to do is I'm going to rewrite -1 as two different fractions that say the exact same thing. I'm going to think of this as -1 over +1, which is still -1. I'm also going to view it as +1 over -1, which again is still the number -1. But looking at those two different versions of how we can play with the combinations of positives and negatives, that's going to help me get points in both directions from that center y-intercept. Let's take a look at the first interpretation, -1 over +1. Again, this is rise over run. So if I rise -1, that means I go down 1. If I run +1, it means I go right 1. So down 1, right 1 is the pattern for that first fraction. And while I do need just 2 points to create my line, I know that there's a lot of space here, and the more accuracy I get, the better time I'm gonna have finding my solution. So I'm gonna go ahead and continue that pattern of down 1, right 1. And I'm going to get in front of it so I can make sure I'm lining up as well as I can. But we're just going to continue going down 1 and right 1. And now I've run out of room going that direction. I want to try and extend into the other direction, and that's where this other interpretation comes in handy. So again, if I had +1 over -1, thinking of it as rise over run, I'm rising up 1 while I run left 1. And you can see that you're still on the same line, but I'm going to continue that same pattern, up 1, left 1, and I'm going to keep doing that until I run out of space. So pardon my reach here. I'm just going up 1, left 1 to get additional points. And once I have all those points, I can grab my straight edge, and I can connect these dots. Now, there's obviously some human error here. These are not lining up perfectly, and we'll talk about that near the end here. But we're doing the best we can, and we're going to put arrows on the end, as we always do for lines, to indicate that the line does continue in this same pattern forever. Now let's look at the red line and do the same thing. Again, we begin with the y-intercept, which is 0, 5, so I don't go left or right, I simply go up positive 5, and I plot my first point for that y-intercept. From there, I use the slope to figure out how to extend. Now, again, the slope is easier thought of as rise over run, so I'm going to rewrite 2 as a fraction. First, I'll call it positive 2 over positive 1, which is still the number 2. I can also think of it as negative 2 over negative 1. That's still the number 2. So there's two different interpretations. So again, rise over run, if I have 2 over 1, that's up 2, right 2, but I don't have space on my graph to do that. So instead of looking at that interpretation, I'll only look at the second. So from this initial point, I'm going to be going down to left 1. So down to left 1, plot a point, and then again, you only need the 2 points to create your line, but I would recommend making as many as possible for that extra accuracy. So if I again go down 2 and left 1, interestingly enough, there was already a point there. Now there's a second point. That's interesting. We'll keep that pattern going. Down 2 and left 1. Down 2 and left 1. And once more down 2, pardon me, in front of your view, and left 1. So again, I've got all those points lining up. I'm going to go ahead and connect them with a straight edge. And while it might not be perfect, the points that I have actually added in specifically, those are helping me to gain extra accuracy, because while I was drawing all those individual points, I did actually notice that those 2 points, both on the blue line and on the red line, were the same. And so that point is where these lines intersect each other. That point is the solution to the system. So the solution is this point of intersection, so we will write the solution as an ordered pair where x is negative 2 and y is 1. And so what this means is that if I were to plug in negative 2 everywhere I see an x, and if I were to plug in a 1 everywhere I see y, both of these equations would turn out to be true. If I plugged in any other value for x or y, either one or both equations would be false. And so this is the only solution that will work. It's the only point of intersection on this graph. So let's take a look at another example and see how this works again. So again, to solve a system of linear equations, our job is to find the point where those two lines intersect. So what I'm going to do again is I'm going to color code this just to help me keep track of who's who. I'm going to make that first equation blue, and I'll make this second equation red, and for each of the equations I do want to graph it. It'll show up as a line. Before I actually get there, let's make sure that we can find the information we need. Both of these equations are already in that slope-intercept form, so let's take a look at these equations as they are and find where is the slope. The slope for this first equation, I don't see the coefficient on x, so that means it's a 1. The y-intercept for that first equation, again, is always written as a point, 0, comma, the constant. So in this case, 0, comma, positive 2. We'll do the same for the red, for that second equation. The slope, again, is that coefficient in front of x. So in this case, the slope is that negative 1/3. And I know we don't like fractions, but when we're doing a slope, it's the rise over the run. So knowing this as a fraction is actually helpful. And then y-intercept, again, is the point 0, comma, whatever the constant is. So in this case, it's 0, comma, negative 2. Let's go ahead and use this information to get our graph. So let's start with the blue equation. That first equation, we begin with the y-intercept, which is 0, comma 2. So I go straight up 2, and I plot my first point. And from that first point, I use the slope to count up or down, left or right, to get additional points. And again, it's helpful to think of the slope as a fraction. So I'm going to go ahead and write this as two different versions. Positive 1 over positive 1 is 1, but also negative 1 over negative 1 is also 1. So let's try and think of it those two different ways. So if I'm thinking it rise over run, positive 1 over positive 1 would mean up 1, right 1. So from this initial point, I'll go up 1, right 1. And because, again, I only need 2 points to get the line, but because I'm looking for real accuracy here to find the point of intersection, I'm going to keep going out as far as I can. So again, up 1 and right 1 to try and gain that accuracy, up 1 and right 1. And so I'm out of room here. Let's now go into the other part of the graph, which would use this other interpretation, down 1, left 1. So from that initial point, down 1, left 1, down 1, left 1, and then I keep going until I run out of room, down 1, left 1, down 1, and left 1. And so I have all my dots lining up. I'm going to go ahead and connect those with a straight line. Again, I am going to see that there is some inaccuracy here because, of course, we're human. Make sure you get those arrows and make sure that you are getting all these points, because with extra points, it'll give you extra accuracy. Even if the line is not perfect, you're still going to see where those points were supposed to be. So let's now look at the second equation where our y-intercept is 0, -2. So we go down to -2 to plot our y-intercept. And then from there, we use the slope to count up or down, left or right. And again, I want to think of the slope as a fraction, which it already is here, but I'm going to write this -1/3 a couple different ways. Remember that negatives can travel. They can stay out in that neutral position, but they also could go upstairs. So this could say -1/3, but the negative could have also traveled downstairs. So it could have said +1/3. Every one of these say the same thing, but it's just different ways for us to visualize it to help us see rise over run. So let's look at this -1/3, thinking rise over run. We're going to go down 1, right 3. So from this initial point, down 1 and right 3. And I actually don't have space to put my other one, so I'm just going to leave it. Let's now use the other interpretation, which would be up 1, left 3. So up 1 and left 3 would actually put us right here, which happens to overlap another point we saw on the blue line, which is a good thing. But I'm out of room again, so I'll just take these 3 points and connect the dots. And again, it might not be perfect, but because we were identifying specific points, I was able to see there was a specific point that did show up in both of these lines, both the blue line and the red line. I had this point here where they intersected, and that point again of intersection is where we find our solution. We'll again write it as an ordered pair, as a point, because it is a point of intersection. We want to make sure we continue to emphasize that. So this point would be going left 3, down 1, so the point is -3, -1. Again, that's our solution to the system, and what that means is if x were -3 in both equations, and if y were -1 in both equations, then both those equations would turn out to be a true statement. Now, the 2 examples we've seen so far have been kind of nice because the equations have been presented to us in that slope-intercept form where we could immediately draw the slope and the y-intercept information straight from those equations. But let's take a look at an example where we have a little bit more work to do up front. Now, the last 2 examples had systems of linear equations which were already written in slope-intercept form, and so they were really easy to get the graph from right away. In this example, we have 2 linear equations which are in standard form. And so our first job, before we can get to the graph, is to rewrite those standard form into slope-intercept form. So let's take a look at this first equation here. We have x minus 2y equals -2. And now that's in standard form where x and y are both on the left side. We want to change that from standard form to slope-intercept form, so I want to get the y isolated on the left. To isolate the y, let's first relocate the x. Since it is currently positive, we will relocate it with subtraction. So we'll subtract x from both sides. That cancels it from the left. And then on the left side, we have the -2y. On the right, we now have the -x and -2. Now to isolate y, we need to detach that -2. Since it's currently attached with multiplication, we'll detach with division. So we want to divide by -2, but we have to be careful to do it to both sides, and not just both sides, but every term on both sides, whether or not it's convenient, does need to be divided by -2. So -2y divided by -2 is just y. And then -1x divided by -2 will give us a positive 1/2 x. And then -2 divided by -2 is positive 1. And so taking that first equation and rewriting it in slope-intercept form by isolating that y, it's now going to be easier for us to see the slope and the y-intercept to help us get the graph. So I'm going to go ahead and come up here. I'm going to erase that standard form away, and I'm going to instead write the slope-intercept form, which was the y equals 1/2 x plus 1. And now let's work on the second equation and do the same thing. So the second equation is written in standard form. We want to write it in slope-intercept form. So we'll begin with the 3x minus 2y equals 6. This is where it's standard form where the x and y are together on the left. With slope-intercept form, we want that x to relocate to the other side. So since it's currently a positive 3x, let's detach this with subtraction, and we'll relocate it then to the other side. So the 3x's are now gone. We have negative 2y equals, and then on the right we have that negative 3x as well as that positive 6. And then our last step to isolate the y is to detach that negative 2. Since it is attached with multiplication, we will detach with division, being careful to divide every single term on both sides by negative 2. So negative 2y divided by negative 2 is a positive y. Negative 3x divided by negative 2 is a positive 3 over 2x. And then positive 6 over negative 2 is negative 3. Okay, so I'm going to take that slope-intercept form from our second equation. I'm going to go ahead and bring that up here. So we have y equals 3/2 x minus 3. So now that I have slope-intercept form for both of these equations, I can more easily see the slope and the y-intercept on both to be able to graph. So for that first equation, which I have in blue, the slope, or the number in front of x, the coefficient in front of x, slope is 1/2. The y-intercept for that same equation, it's always written as a point, 0, comma, whatever the constant is. So in this case, it's 0, comma, 1. And then for the second equation, which I have in red, our slope is 3/2. It's that coefficient in front of x. And our y-intercept, again written as a point, 0, comma, the constant, in this case 0, comma, negative 3. So I'm going to take these pieces of information to help get the graph, and once we have the graph, we'll have two lines and we'll see where they intersect. Let's begin with the blue equation, the first equation. We begin with the y-intercept, which is 0, comma, 1, so I'll go ahead and put my first initial point there. From there, I use the slope to count up or down, left or right to get additional points. And for that slope of 1/2, I can think of it as positive 1 over positive 2. I also can think of it as negative 1 over negative 2, and both will be helpful to extend this graph in both directions on both sides of this y-intercept. Let's start with the positive 1 over positive 2. Again, if this is rise over run, I'm going to rise up 1. I'm going to run right 2. So up 1, right 2. Gives me a second point, and I do just need 2 points to create a line, but I want more accuracy, especially when I'm solving a system and the points really matter. That point of intersection is going to be very important. So let's continue to rise up 1 and run right 2. So up 1, right 2. At this point I'm out of room, but if I go in the other direction and instead go down 1, left 2, I can get additional points this way. And I'll go again, down 1, right 2. And now it looks like I'm out of space, but I will take those points, I will connect them with a straight edge here. And then I will use arrows again to imply this pattern continues forever. Let's now look at the second line, which we have in red. We begin with the y-intercept, 0, comma, negative 3. So I go down to negative 3 to plot that first point. And from there I use the slope to count up or down, left or right. Now that slope of positive 3/2, I can think of that as positive 3 over positive 2. I can also think of it as negative 3 over negative 2. Let's think of positive 3 over positive 2 first. So from that initial point, rise over run, I can go up 3, right 2, up 1, 2, 3, right 2 would put me here. I could do it again, up 1, 2, 3, right 1, 2, and coincidentally I wind up overlapping that point. And then I'm out of space, I can't go up 3. If I tried the other version, down 3, left 2, there's no space for me to do that there either. So these 3 points, it looks like, is all I've got. I go to connect them. with a straight edge. And again, remember you want your arrows to say this pattern continues forever. And so now I have my two lines from my two linear equations, and my job when solving this system is to find where these intersect. And since I was so good about identifying specific points as far out through this graph as I could, I was able to very clearly see that this point here was an intersection point. That's going to be my solution. It's a point that appeared on both the blue line and the red line. That's my point of intersection. So it looks like that point is to the right 1, 2, 3, 4 and up 1, 2, 3. So my solution here is 4, 3. And if I were to plug in 4 everywhere I see an x, or plug in 3 everywhere I see a y, both those equations would turn out to be true statements. So we've seen 3 examples now where when we graph the lines, we get one point of intersection. But there are some funky examples where we get some different kinds of pictures where we don't see that one point of intersection. So let's take a look at an example like that. All right, let's try this last example here. For the first equation, I see that it's not written in slope-intercept form, so I'm going to go ahead and go off to the side here and take that 3x minus y equals 4, and I want to rewrite it in slope-intercept form. I want that y by itself. So first thing I'll do is I'll relocate the x. Since it's currently a positive 3x, I will subtract 3x from both sides to relocate it. I now have negative y on the left side. On the right, I have negative 3x with that positive 4. And even though y is almost by itself, it's not quite. There is a negative 1 as a coefficient attached to that y. It's attached with multiplication. Let's go ahead and divide everything by negative 1. Make sure that you do it to both sides to maintain that balance. Dividing by negative 1 really just means change everybody's sign. So negative y turns positive, negative 3x turns positive, and positive 4 turns negative. And so that first equation, let's go ahead and rewrite it with its slope-intercept form of y equals 3x minus 4. Let's also do the same thing to the second equation. It's also not quite in slope-intercept form. It looks like it's in standard form. So let's take that second equation and let's rewrite that one. So let's take that 6x minus 2y equals 0, and let's rewrite it so that y is isolated. First I'll take the 6x, which is positive, and I want to relocate it away from the y, relocate it to the other side. So we'll subtract 6x. We then have negative 2y on the left, and on the right I have negative 6x, and I don't need to say plus 0 because that's not really all that important. And now negative 2 attached to y with multiplication, we will detach with division. Make sure we do it to both sides. Now we have y equals positive 3x. So this equation shows us the slope. It doesn't show us the y-intercept, so we'll talk about that in a minute here. Let's rewrite our equation in its slope-intercept form, y equals 3x. So now that they're in slope-intercept form, we can gather the information we need to graph them. We can see the slope, we can see the y-intercept pretty clearly. For that first equation, which I have in blue, the slope, which is the number or coefficient in front of x, is 3. The y-intercept, which is always written as a point, 0 comma, the constant, in this case 0 comma, negative 4. For the red equation, the second equation, I have a slope of 3, that's my number in front of x, and then I have a y-intercept that I don't see. The y-intercept is supposed to be the point, 0 comma, the constant. If I don't see a constant, it actually was written before as plus 0, and then I just kind of took it off because to say plus 0 doesn't really add anything to it. But really the constant is 0, so the y-intercept is actually 0 comma 0 in this case. And in these two lines, we notice the slope is the same. So let's see what that looks like visually. Some of you who have graphed before may know what's coming, but let's see what happens. Let's start with the blue line. We will begin with the y-intercept, which is 0, negative 4. So down at -4, I'll plot my first point. From there, I use the slope to count up, down, left, right. To get additional points, let's think of 3 as a fraction. Let's think of it as +3 over +1, or if needed, we can think of it as -3 over -1, both of which say 3. Let's try the +3 over +1, rise over run. We're going up 3, right 1 from this initial point. So up 1, 2, 3, right 1, up 1, 2, 3, right 1, and up 1, 2, 3, right 1. And I'm out of room this direction, but I also don't have room in that direction, so I'll just go ahead and take these 4 points and connect them with a line. Again, make sure when you connect your points, you are using arrows to say that this same pattern continues forever. Let's look at the other line, which begins at the y-intercept 0, 0. This is the point called the origin, where our x and y axes meet. And our slope is again 3, so again we can think of this as +3 over +1, or we could think of it as -3 over -1. So let's start at the initial point, the y-intercept, and go up 3, right 1. 1, 2, 3, up, and right 1. And then I don't have room to go up another 3, but let's try the other interpretation, which was down 3, left 1. So from here I can go down 1, 2, 3, and left 1. And then when I connect the dots, there we are. And again, remember your arrows. So now we saw that the slopes for these two lines were the same. And remember, slope is steepness. When I drew these lines, they have the same steepness to them. And as long as the arrows are here telling me, hey, this steepness, this pattern continues forever, these guys are always going to be at the same steepness but separated from each other, and they're never going to change steepness to run into each other. These lines will never intersect. And so if I'm looking for the solution to the system, which is the point where the lines intersect, if there is no point where they intersect because these are running parallel, then there is no solution. So this is a weird case where we see no solution at all. And we have a special name for a system which has no solution. A system which has no solution we call an inconsistent system. Just a fancy name we give it. If it has no solution, it's an inconsistent system. So if ever you have lines which have the same slope, but they have different intercepts, different y-intercepts. They are different lines, they're not the same line, but they run parallel to each other. If they're parallel, they will never intersect, and so there is no solution. Now let's just suppose, instead of being parallel lines, what if they were actually the same line? So let's just pretend when we went through this second equation and changed it to slope-intercept form, what if it was in fact y equals 3x minus 4, and they turned out to be the same line? They would have the exact same slope and the exact same y-intercept, and so then when you graphed them, you would wind up with the exact same line overlapping itself. So where do those lines intersect? They intersect everywhere on this line, and there are infinitely many points on that line. So if that were the case, you'd have infinitely many solutions, and we would call a system like this, where the equations are technically the same, we would call that a dependent system. So on your homework, you may have some drop menus that ask you, is this an inconsistent system with no solution? Is it dependent with infinitely many solutions? Or is there just one solution? And if so, what is it? So just a couple different weird cases. Now, beyond these weird cases of the inconsistent no solution or the dependent infinitely many, even when we were looking at one solution, I'm sure you can imagine not every solution is going to turn out to be a nice whole number. Sometimes you're going to have examples where the numbers are so large you don't really want to graph it. So we have to have some other techniques for solving systems, and that's what we'll be looking at in the next two videos. We're going to look at system solving techniques called substitution and elimination. They will be algebraic ways for solving instead of graphic ways for solving, and it will help us to gain a lot more accuracy, and it'll be a lot easier when we have examples with larger numbers or fractions.